Andre Mahali, and he's going to be talking about building elastic and cloud-ready apps. This will probably go on for about 45 minutes to an hour, but if you've got any questions, do let us know. You can send in your questions, and I can interject and let Andre know when it's a good time. Otherwise, there'll be probably a little bit of time at the end as well if you want. So fantastic. All right, Andre, as soon as you're ready, you go for it.
Yeah, thank you, Jaden, for the fast and
yeah.
precise introduction.
Yeah.
So I'll start. I'm going to talk about how to develop applications for clouds to be scalable and match the requirements that we have in modern applications. But first, we need to step up backwards from to realize what we need. So I'm going to talk about how to think about evolution of your application before we get to the clouds. So I'll start sharing my screen, and before everything, we should realize what we want to do. What is actually cloud-ready app? If we want to develop a cloud-ready app, and then also whether we really need it, at least in the start. So here are a couple of technologies that people might think of when somebody mentions cloud. But let me stop for a while. Do you really think the technology is what's necessary to make your application cloud ready? Is it really about technology? We have many cool technologies. A lot of them start with K. Before they started, we used to start with J to refer to Java. Now we have more than Java in the world, in the technology world, and in the cloud space. So we have a lot of these things, but we have to be careful because these things might be cool when we read about them, when we play with them, but they may not be so cool when we want to use them and beyond that, so tune for production, tune to meet the requirements we have. So be careful, because before you will have to use another word that starts with F, and that's not so fun. It's not fun. Let's pause for a while and not talk about technology. Let's talk about requirements on our applications. And typical cloud-ready applications that should be or are candidates to be deployed into the cloud have usually scalable requirements or requirements of scalability. So it means you may not need the resources now, but when you need them under a higher load in the future, the application should be able to absorb the additional resources and handle the load flexibly. So there are some of the most important things I will focus now on in this presentation are on these slides. There are more of them described in the 12-factor manifesto, which also include things like continuous integration and delivery. I'm not going to talk about these now, but I'm going to talk about things that you would use when designing your application, not the whole pipeline of developing the application and deploying it to the cloud and configuring for production. So this is all you need to think about when you have clouds in mind, but I will be focusing only on the first initial part to get us started. So applications typically need or should have pluggable services. This means that you should be able to inject any service into your application and even replace it with another implementation or another service that is maybe better better suitable to in the cloud scenario. So for example, initially you might need just a small database and maybe a database to make it easy to develop with. And later, when you deploy to the cloud, you might need to switch to a cloud-hosted database, or even a different type of database like Amazon Dynamo, which is not SQL database. So you should be prepared for this. You should put an explicit boundary between your application and the resources, and make it easy to plug away and plug in resources, ideally without changing your application, or at least with changing your application in a moderate way, so that it's possible to do these things in the future. Your applications should be also scalable according to the load, as I mentioned. So it means you should be able to start multiple instances of your applications, and also access multiple instances of database. So nothing can be statically configured and hard-coded in your application. Everything should be configurable. Everything should be designed with elasticity in mind. Never think about accessing one single instance of a service, because there might be more services and you would need to have some load balancer in between and things like that. This leads to low coupling, which means your services should be distinct, and it should be possible to link them together in different ways, even deploy them separately in different data sensors if needed, or different infrastructures. If, for example, you need to mix services from one cloud provider with services from another cloud provider, you should be able to do that. If you have a monolith, it's not possible to deploy the monolith in two different places. This can be powered by an external configuration. So ideally, configuration is very lightweight in your application, and everything can be configured externally. Your application should be able to recover from failures, because in the network environment, there are a lot more failures than in isolated monolithic application. And also you have to secure the communication, which is another addition, another bonus in distributed architectures. And it's also important to monitor. It's easy to monitor a monolith, where especially on JVM, you have a lot of monitoring options inside the JVM. And even if you add more monitoring options, you would still monitor one JVM, one process. In distributed environment, you have to collect metrics and monitoring data from multiple different services. So let us think about the solution. I would say that the solution is to pick good abstractions on top of existing technologies, and first think about using simple technologies behind these abstractions, and make the technologies pluggable, so you can later decide what you need to improve and plug in a more sophisticated solution without changing too much of your application that is on the other side of the abstraction. So you should focus on continual evolution of your application. You should think about designing components that are clearly separated. Ideally use what is available by your platform, your framework, any APIs that you can plug in and that you can provide with some implementations. And here is a very good, here you can leverage the value of standards, because if there are standard APIs and multiple implementations for them, some implementations are more convenient for your use case. Maybe some of them are convenient now, but maybe later you would need something more powerful, or with certain aspects that you didn't know before. So it's good to focus on existing standards, pick them, use them, and later decide which implementation is best for you. And if nothing is good for you, you can even create your own implementation if you really need. But it's a good start to have something to work with behind a clear abstraction. This would allow you to focus on application logic first, because you have a lot of APIs that you can reuse, and you don't have to be afraid that these APIs would have to be removed or rewritten, because you can easily replace their implementations without rewriting the rest of the business logic. And also it allows you to write down the business logic without all the boilerplate that is needed to keep the technologies together. So let's see what is maybe an ideal cloud architecture. This is how I see it, that every application should have something in mind, should be described with components like these. Not all the applications require all the components, but this is a general schema which provides a lot of flexibility, either for your own local development deployment or later when they're deploying to the cloud. So you need something that powers your applications, the services basically that you tie together to form whole application. To communicate between them, you either use direct protocols like REST, or you have a distributed message broker. It's important to have a message broker that is distributed. This is in the cloud. In your local environment, you don't have to have a distributed message broker. You don't even have to have a broker per se. You just need to have some mechanism that does the job of delivering messages from one service to the other. So if you think in these layers, from simple development or your local computer to maybe some performance testing, and then later to adding scalability in the cloud, you may be able to pick different solutions for different stages of your project. And if you have good abstractions, you can later, with very small effort, replace the technological or the technology and change your technological decisions. The same as for message broker is for persistence. It's ideally is also distributed, but you don't have to start with distributed persistence. You don't have to have a reliable persistence during development. You can have something that just works for you during development. So let's start first with persistence. Persistence is what most applications need, and I argue that there are basically two standards for Java applications for persistence. One is SQL, which already requires some SQL application, some SQL database. Maybe we can start with an embedded database, but you already need something running in your application or next to your application. And the problem with SQL is it's not very reliable standards. Some databases implement different versions of the standard. Some implement it in a different way. So you have some variance, but it's still a good start to write persistent code or to save that data. But another option is not so obvious, but I want to focus on it more. It's JCACHE, and why it's so good to start with. It's much more simple than SQL. It's native to Java, so you don't have to translate from Java to SQL, and it also provides persistence. caching is not only about improving performance and keeping data for some time, but you can also turn cache into memory storage. And because JCACHE is a standard, there are multiple implementations of caching, and a lot of them are distributed. And they are very cleverly distribute data across different services. They provide a lot of options for scaling and replication of data, and they're much easier to use than SQL database if you want to scale them to multiple services. That's why I recommend starting with JCACHE for proof of concepts, and maybe you won't go further because you will need just a small service that stores something in cache for some time. If you need to store JCACHE, the data stored in JCACHE, you can also add listeners on cache, or what is called write-through and read-through listeners, which allows to persist data that is stored in the memory in JCACHE, and also deal with the data when it's removed from JCACHE. So we could use JCACHE to create an abstraction around our distributed data, and later when we need to really store them in an SQL database, we could just either extend JCACHE with the listeners to store data in the database, or just replace the caching mechanism with some JPA or some object relational mapping. JCACHE is a mechanism for basically storing key value data, so it's similar to other key value NoSQL databases. The only difference is that there's no guarantee about keeping the data in the cache, or the JCACHE standard doesn't really ensure that the data is persisted on database. So in Payara Micro, there is already an implementation of JCACHE built in, so you can use it automatically in the application. You just need to add the JCACHE API dependency, and it's there. And code like this would build and run on the Payara Micro or Payara server, and would already store data in database, or that's so-called database in a data grid that is powered by all the instances, all the Payara server or micro instances on the same cluster. So it already gives you a lot of persistence on until you have at least, or as long as you have at least one instance running. You can have one master instance running all the time on a remote server, and always connect your cluster to the instance, and you would still have the data. JCACHE is very easy to use. You can just annotate methods with annotations like cache result or cache put, cache key. So you can turn a regular method into a method that stores data or retrieves data to a data grid. Or you can get the cache interface injected and then use it to manually put and retrieve the data into the store. You can even iterate through the data and filter the data, which is quite fast. It's not so optimized as SQL, so it still need to iterate over through all the data. But since all the data is either on memory or very close on the network, it might be still often faster than going to a database and running an SQL query and retrieving the data from the JDBC driver. So as I said, JCACHE is often available out of the box in application containers. If it's not available, there are many implementations, and even if it's available, you can still replace the implementation by your own implementation that you choose, and you don't have to replace or modify your code in your application. The second step is to have a scalable runtime. So first we solved the problem of scalable persistence. Now, if we want to have or build an application that is easy to develop and still allows scalability in the future, it's good to have a runtime or a server, something that runs your application and allows to run it multiple times and connect it together so that it can communicate without doing much or without too much work on the developer side. So for this, here it fits in the picture. Payara provides a very flexible runtime to run your applications, but it's not the only option. You can use a lot of options that provide Java EE or MicroProfile APIs. Then there are options beyond these, which for example, Spring Boot, Vertex, or Micronauts. These are frameworks that provide these. So you can pick any of these if they provide scalability and are easy to use and provision. But Payara Micro and Payara Micro is an option when you want to really rely on standards. As I said before, standards are important to have the options of replacing what you have under the hood with something more powerful or more convenient for you. With Payara Micro, you already start with something very powerful, but it might be too much in some cases. You might need to switch it for another implementation that starts faster and doesn't provide anything beyond the API for the application. But Payara Micro is a good default choice when you want to start developing your applications, because it provides a lot of features out of the box, and you don't need to think about where to get those features from other dependencies, from libraries. There are a lot of services in Payara Micro that allows you to debug and monitor what's going on in your application during development and troubleshooting. There are other things on horizon. Jakarta EE project is a continuation of Java EE project within the Eclipse Foundation, and we hope to see more development on this project in the future to complement the fast development of MicroProfile APIs. And then, as I mentioned, there are some implementations that you can choose instead of Payara Micro if you want, or if you're afraid that you would be stuck with Payara Micro. You won't. you can replace any with any of the MicroProfile implementations or Java EE implementations. Here is a summary of what Payara Micro is. I believe a lot of you already know. If you don't, I will showcase in the demo at the end. The important thing is that it allows you to scale your application very fast. You can just start your application from command line. You can use the same command multiple times, either on the same computer or different computer network, and the instances will just start and connect to each other, so they will know about each other, and you can communicate between them with some useful services that I'll come to later. I already mentioned MicroProfile. Just here to summarize, it's another set of specifications or another set of APIs that somehow complements or builds on Java EE standards. It just takes some Java EE APIs, so it's not an extension to Java EE. It's more like a complementary set of APIs that's built on some common foundation, but it fits well together. So, for example, Payara Micro and Payara Server 2 both provide both of these standards, or Java EE and MicroProfile mix well together. So together, these standards provide a lot of abstractions that you don't need to think about when you want to just develop an application. You're free to do business code, and some of these things are even provided out of the box without any effort. For example, metrics, which is a standardized endpoint provided by all MicroProfile implementations, and it provides some insights about default metrics. You can provide your custom metrics within your application to enhance the value of these metrics or the standard. But even when you deploy any application on Payara Micro, will get some set of standard metrics like CPU usage and memory usage. Then there's also Open API standard, which will provide documentation of all the REST services you have in your application. So again, you can customize this, but you don't have to do anything to provide some documentation out of the box. And then there's open tracing and health, which are provided, or some functionalities provided out of the box for any application using MicroProfile. So we discussed persistence, we discussed services. Now we need to get to how they communicate with each other. One way of communication is point-to-point communication, where RESTFUL is a de facto standard in this area, at least in the cloud and in services. Not talking about IoT, where maybe HTTP protocol and JSON is a little too chatty. But in enterprise applications in the enterprise world, RESTFUL is very common. And it's already a good abstraction, because it's a rather clearly defined standard, and any programming language supports it. But if you would like to support it in Java application, you don't want to write it from scratch. You could access external services by HTTP client, but if you want to expose an external REST service, it's good to have some framework to do that. So let's put REST API between our services to communicate. Payara Micro provides Java EE standard. So if you, or Java EE API for communicating with REST services and exposing REST service endpoints. This is a standard within Java EE, and it's also part of MicroProfile. So even in just implementations which offer only MicroProfile and not Java EE APIs would also support this. And it's very easy to turn any class into a JCACHE endpoint just by adding some annotations. This is very powerful because you can very easily unit test the class. You can create a class first to be used inside your application, and then when you want to split part of your application to another service, when, for example, when you start with a monolith, which I would always recommend for new projects, you would start with a small monolith, and when it grows too much and you feel some functionality should be extracted to a microservice, then it's very easy to turn a business object into a REST endpoint, so that you can call it from the original application into the new application, or vice versa. There's also an API to read data or communicate with REST endpoints, which is in JCACHE is not so straightforward and not so abstracted. It's quite programmatic. It's powerful on one side. On the other side, it relies on the JCACHE's API, and it's not so easy to use. But then I don't have example of it. But MicroProfile has another abstractions which is even nicer, and this is called type-safe REST client, which even from the name hints that it allows creating type-safe interfaces. And a MicroProfile foundation is capable of turning all the interfaces annotated with the JCACHE annotations into client stubs. So you can basically then turn any interface or any class which you had originally in the monolith, you can separate its interface and turn the class into a REST endpoint and take the interface to the other service and turn it into a client proxy without too much coding. Just adding JCACHE annotations or JCACHE's annotations on one side or the other side. So that's quite nice. JSON binding is another nice API, which is also present in both Java EE and MicroProfile, and it allows abstracting serialization of Java objects to JSON. So this is again useful when you want to split a monolith into microservices. You take an object that is used as a parameter to method calls or a return value from method calls. You add JSON binding to the same object, and then you can use it to serialize to a REST call and then deserialize on the other side without changing your business logic. For callers, for clients, it will still be a Java object and a Java service implemented as an interface, and on the other side, the server side would again get a Java object from JSON. Yeah, Jaden, do we have any questions? Just checking in.
No, not at the minute that I can see. No questions.
No, that's good. I don't see anything right now, just my presentation. So I'll continue. If you have any questions, raise it in the chat. I'm happy to answer. Yeah, so we covered point-to-point communication. Now we can get into messaging. And messaging is very important in cloud architectures, even more important than point-to-point communication. The thing why messaging is not being talked about so much is, I think, because it's more complex, and it's not easy to get right, and also it's different to what we it's harder to reason about because it's asynchronous. You don't get the response when you need it, you get the response when it's available. So compared to calling a REST point, you get the response when the data is available, but you stop execution and you wait for the response. So it's easy to process everything after you get the data. You just wait for the data, you get them, and you continue processing. With messaging, is not that easy. You just send a message and you have no answer until you have the answer. And very often you don't have the answer at all. You know from the real world when you send a message to a colleague or a friend, and then you ask them if they know about this, and because you're sending them a message, and they ask you, what kind of what message? I didn't get the message. You know, it may happen, and this is real life, and also in applications and in technology, it's the same. You have to make sure that the message is delivered. If it's not delivered, you might have to send it again. But it's also very important because it allows scaling much more. It allows scaling much better than applications designed with point-to-point communication. because messages can be processed in parallel at any time the other side has throughput or time to do that without waiting, and the caller doesn't have to wait, can do something else meanwhile waiting for a message. So it's also similar to a real life situation. When you want to ensure that your friend got the message, you would call them on the phone, but then it's the only thing you can do. It's very easy, hard to do anything beyond just watching something when you're on the call. But when you text things, you just text it, and then you can do anything else. You can even text multiple friends in parallel. You can have multiple chat windows and text with them together. But having all of them on call is not possible. You can only have one. So, as I said, messaging is very useful, but not that easy to do and not easy to work with. So what I would recommend is to start simple. And the simplest API that still kind of relates to messages is CDI events. CDI events is a standard within Java EE and also MicroProfile. It's basically about dependency injection, but it also contains a mechanism for sending events, because you can just inject event sender on one side, call a method to send an event, and on the other side, a method is called on observers. And this is all powered by dependency injection, because the dependency injection mechanism chooses which event sender is injected on one side and which bean listens for the events on the other side. So it fits quite naturally into dependency injection. It's just something more, but it's very powerful and easy to use. The downside is it only works within single JVM, so it's not very convenient to really send messages across the network, because it doesn't work. It just sends messages or sends events between components within a monolith, within a single service. But we can, or can we, extend this to a messaging system? Yeah, basically, yes. If we don't need transactions or reliability with external message broker, we just need to provide a different implementation for CDI events. And it's possible to observe events in one application, then wrap them into messages and send them all across network, where another service would again trigger them as CDI events that could be listened by your application across the network. So the only missing piece is the bridge between CDI events triggered locally and listened locally, and between listeners across the network. As an example, Payara platform offers a CDI event bus, which is a built-in engine based on Hazelcast, which provides exactly this. It allows you to raise a CDI event in one application and then catch it by Payara Micro, transfer it over the network using Hazelcast to any Payara Micro or Payara server instance on the Hazelcast or on the cluster, and trigger the event on the instance in a different instance of your service, or even in completely different service. It just has to be the same type of event and same qualifiers, and obviously if it's going to be transferred over network, it has to be serializable. This is especially useful when you want to have some engine to send messages, to send events across network. during development when you create a proof of concept. It's very useful. During later stages, it might be enough for you if you don't have to rely on transactions, and if you don't need a reliable broker or reliable messaging system. This might be very often the case because applications and cloud have very different expectations or requirements than what we were used to before. For example, applications that are highly data-driven and process lots of data and create aggregate data based on this data, they wouldn't care so much if some small portion of the data is missing, because it wouldn't affect much the aggregate results. But if you are building something in the enterprise world and you have to be 100% certain about the data and not losing any piece of data, you can still develop using this CDI bus and later exchange the mechanism for something more powerful. The important thing is that the CDI specification and the CDI events are very nice abstractions over sending messages across the network, because they identify the message and the sender and the type of receiver based on qualifiers, based on the message type. And you can even give a name, so it you can do something like named queues. You can name your sender and receiver, and the CDI bus would only send messages to matching pairs. When you need to grow, you can use some other standard, which is JCACHE connector. This is again a standard that you don't have to, or you can use with a lot of implementations. Although you might, it's not a standard that is clearly abstracts all the implementations from your application, and there's a value to that, because if you want to use powerful mechanisms, you very often want to use their in unique features. So abstracting everything away would take power from you to take. Wouldn't enable you to make use of the features in the messaging systems. But still, it's a good abstractions to start with, and if you want to choose different implementations, you still wouldn't have to change a lot of code in your application. Maybe you would change the interfaces slightly, but the overall functionality would be very similar, and code changes required wouldn't be so big. You can use JCACHE. A lot of JCACHE connectors out there to plug into the messaging infrastructure of Java EE runtimes. And what actually JCACHE connector is, it allows any external service to be plugged in and routed to a message-driven beam. So if you already know what message-driven beams are about, you might be surprised to know that message-driven beams are not only about JMS and not only about transactions, but they can be tuned to or tweaked to any external connector, to any external system that is capable of producing or reading data, consuming data. And this is very useful if we have these JCACHE connectors to external services. We can just choose the connector for our service, for example, Amazon messaging service or other services in the cloud, or standalone local or standalone services like Kafka or MQTT. And we don't have to change our code so much. So for example, we can start developing against Kafka, which we can run locally, but then later refactor this easily to support Amazon messaging service. The code resembles message-driven beans. And if you know if you were using message-driven beans previously, you would find the code familiar. So where does it fit here? Yeah. Before we had CDI events to communicate, now we can use also JCA connectors. There's a Payara repository which provides multiple connectors for cloud services. Like as I mentioned, Amazon messaging service, there's a connector for Azure service, for Kafka, for MQTT, and you can choose any of them. They work best with Payara, but since they support the JCA standard, they can be used with any Java EE container that supports the JCA standard. But now, why was I talking about CDI events before, and now I'm talking about JCA connectors? Are these competing technologies? No. I wanted to show you that you can layer technologies on top of each other to get more and more into detail, and to pick more and more sophisticated technology without changing the upper layers. If you start with CDI events, you might start with the CDI event bus built in into Payara platform, but you can also replace it with the JCA connector, which would listen to CDI events locally and send data over through the JCA connector to any messaging system supported by the JCA connector. And then on the other side, when the message is received, the message-driven bean would trigger a CDI event in the same CDI event as before. So the difference would be only in the messaging layer, but not in your application code. Here is how it would look like in your application. You start with an event sender and observer, and then you can extend this by adding a JCA client and message-driven bean between those. And for your application, it would still look like a CDI event, but underneath, it would be connected, the services would be connected not with Hazelcast, but with any JCA connector you choose, for example, Kafka or Amazon messaging service. This is the essential idea of evolutionary architecture that very often is Neil Ford and Rebecca Parsons from ThoughtWorks talk about. And I like this concept because it saves a lot of money and frustration in the beginning. And if we build our architectures and applications for future evolution. So if we design our architecture in a way that it's extensible and modifiable in the future, we can save time in the beginning, because we don't have to go into so much complexities in the beginning. We can solve complex problems later, and we won't have so many obstacles in refactoring and modifying our architecture. The last thing I'm going to talk about is configuration facade. This configuration is a thing that ties everything together, and keeps everything running and connected. Again, it's important to have some easy abstraction, which is can be or yeah, where we can use a MicroProfile configuration as the abstraction already. It's also available in Payara Micro and any MicroProfile container, and it fits nicely with Java EE because it provides injectable configuration. So it's another part of the standards or another standard API that allows us to abstract away the complexities and the options we would need later and focus on the business logic, focus on just getting a value where we need it and decide what to do with the value without thinking about how we will provide the value now and in different environments. MicroProfile configuration supports by default standard configuration sources, so we can provide values by environment variables and system properties, and also properties inside your application. This is out of the box, so if you develop an application, you can provide some sensible defaults or even configure some values externally through environment variables and system properties in different environments. If you want to have something more sophisticated, like when the number of your microservices grows and you want to configure them from one place, you can provide a custom config source in your applications, which plugs into the configuration mechanism and reads configuration from external system, for example, a database, or if you want to get secret data that shouldn't be stored on a file or unencrypted in a database. You can have a secrets config source that gets the data from the network, from the secret service. You can have a connector to etcd, which is distributed configuration service, and a lot more. It's very easy to write a config source. You just implement an interface with 2 or 3 simple methods. The most complicated method is to return a value based on a textual key. So this is where you would connect to your external configuration provider, read the value, and provide it to the application. And that's it. Within your application code, you would just use things on the right side of the slide. For example, to inject a configuration of a URL with the key myService URL, you can inject directly a URL object, because the configuration will automatically map the URL value or the text in the form of URL into an URL object if it's well formed. And there are multiple objects types or supported by configuration by default. Not only specific types like URL or string or integer, but any type, any class that contains string constructor or parser method that accepts a static parser method that accepts a string value. So you can easily create mapping from a configuration for value to any object just by implementing or adding a static method value of or parser. If it's not enough and you need to do something more sophisticated, or you can't modify the class, you can also provide a mapper, which is, I forgot how it's called, the interface, how it's called, but there's, you would just implement an interface that would convert string to a value and that's it. And provide it with a service loader mechanism. To to read the values programmatically, if you don't want to inject it or can't inject the value, you can get an instance of config interface, config object from config provider statically, and then read the value and convert it, for example, to URL class or any class you'd like to have. So I'm close to the end. Switch to the demo. How much time we have? Not much. So do we have any questions?
No, no questions that I can see at the minute.
Okay, so I'll just quickly show the concept of extensibility of the application, because I don't have much time for anything else. Here I have a simple application that contains that is composed of two services. One is producing data, and the other one is listening to the data, is receiving the data and sending them to a browser. It looks basically like this. I think I've stopped the application, so it's not moving. But the web browser will just get the data as it comes and update the graph. The important thing is it's two different services, so they have to send messages, and there's not just one application generating the data and sending to the browser. So let's now start our producer. It's a Payara micro application, which is basically just a WAR application with WAR Maven project. And I started with Payara micro Maven plugin. The most important thing is the stock producer, which just for demonstration purposes generates some random data. And in order to make it isolated, it just fires an event and then doesn't care about who will handle the data and how it will be transferred. So here we will use the CDI event, inject the sender, and fire the event from the code which is scheduled every second. So this will be then routed to whatever observer is matching. And the power of CDI is that to match it with, or to send it through the CDI event bus in Payara micro, you just need one annotation to mark it as a special type of event, which should be transferred through a Hazelcast to other Payara instances on the cluster. That's it. On the sender side, you just need to use this outbound annotation. We will come back to the Kafka annotation later. On the other side, we have an event receiver, which is again just a CDI receiver. It's a method with annotation observes on the parameter stock, and to get it from the CDI Hazelcast bus, which is annotated with inbound. So this means that anything that is received from the cluster is sent to this receiver if it matches the type and possible qualifiers, which I didn't use. So these two annotations are all we need beyond the CDI standard to transfer events from one service to the other service across the network. I'll start also the receiver. So if I refresh the page, I should be, it takes a while. It's taking so much. Oh, it's there. So you see that we're getting events from the other service. If we stop the service, we stop getting events, but the application is still there. It's still live. It just doesn't show the graph. So I won't go into much detail because we don't have much time, but I will show you how you can develop this application further to provide a Kafka messaging system instead of Kafka, or to send messages over Kafka instead of the CDI bus. So there's some boilerplate code needed to send messages through Kafka with the JCACHE adapter. This is very similar to sending messages over JMS. You request a connection factory with the specified JMDI name, configure it in the connection factory definition. Here are some properties like the URL of the Kafka broker and the resource adapter that we also need to add into our runtime. So we deploy, if we look at the log, we basically deploy two deployables. I don't see it right now. But when you start Payara Micro, it will say two applications deployed. If we look into POM.xml, where we configure the Payara Micro plugin, we are adding some libraries required by Kafka connector, and the connector itself as a RAR file. So we deploy it as an application, very similar to our application. It's just not application, it just plugs into the runtime. It has to be deployed before the real applications, otherwise there will be a missing dependency in the application. So the second thing is our application, our RAR application deploys. And here I already prepared a Kafka qualifier, which is just my custom qualifier. Is an annotation with the CDI qualifier. It means that CDI will pick this up. It won't use the outbound annotation because I delete it, but it will send it to an observer that receives for events marked by the Kafka annotation, which is basically my publisher. The publisher will receives the event. Instead of the event going to the CDI bus, it will go to just locally to the publisher, and the publisher will convert it to a Kafka event and send it to the Kafka broker. For this to work, we need to start Kafka. If we don't start it, then the messages won't go anywhere. So I start it now, and I will redeploy my application. And now we should see the messages coming to the Kafka browser, Kafka broker. There are some messages coming. And in order to receive them on the other sides, we need to define something more than just a CDI observer. We need to define a messaging bean that listens for messages from Kafka, again some configuration with activating properties. It implements Kafka listener, which is an API we need to add to our application, but it's only API, nothing in our application. The real work is done by the JCACHE connector, which again has to be deployed before our application in the same way. Yeah, here it is. So here we again deploy the RAR file and the var. And inside the MDB, to continue with the CDI abstraction, we just fire an event. The same stock event, we just mark it with Kafka again. And here in the endpoint, we will replace the inbound qualifier with Kafka qualifier. So after everything is in place, to apply it, to really apply it, we just need to switch the outbound and even inbound annotations to Kafka annotations in both producer and consumer. Now, when I apply the code changes, and hopefully everything works. When I refresh the application, it may take some time. I need to restart. Yeah, so that will be it. Once the application starts, it will suddenly route the messages through Kafka broker and not through CDI bus. But the only thing I needed to change is just switch the annotations. The rest of the application doesn't even need to know about this stuff. Okay, now we're receiving the messages. Yeah, and everything looks like before. The only difference is that now it goes through Kafka. So if we, if we stop the Kafka broker, we stop getting messages. Okay, that's it basically. The only thing, the other things I wanted to mention is that we have a lot of bonus with the standards, especially with MicroProfile, which provides the monitoring health and open API, which I mentioned before. And yeah, these are really free editions, except they only provide basic data. If we need to tweak them more, we need to add some configuration in our application, some annotations to add more information for these systems. And there's a lot more in standards which we can use, like fault tolerance, if we want to introduce more resilience into our applications. So there's a lot to apply beyond what I explained. But these 5 things that I was talking about provide a good base. And I hope that they will illustrate how to apply the same concepts in other situations. For more information, you can look into these links, and that's basically it. So thank you. And since you, I believe, do we have any question now?
Just having a look. No. No questions here, and no question in the chat. I can't see any hands raised either.
Okay, so if you have any more questions later, feel free to contact us. We are always there on the internet, either on Twitter or via forum, anywhere. Thank you.
Bro, thank you very much, Andre. Thank you very much, everyone.